We are on the example number 41 on page 365. So in this example, two objects move as shown in the figure. So you can see v1 and v2, there are the velocity vectors. They show the direction of the motion as well. And object 1 has a mass of 6.5 kilograms and object 2 has a mass of 3 kilograms. Determine the angular momentum about the point O. So point O is origin, right? So we're looking for the angular momentum around that point. That point could be like a pivot point later on. Is just like rotate, if there's a rotation or something. But again, you don't really need a rotation to find angular momentum. Okay, so but you need to be given where you're calculating it from. If it is not obvious, like you have a pivot point or something, then that's why they're telling us that let's measure everything from that origin. Okay, so we have xy plane. Both of the masses are on that plane. So we have two moving objects, and we are looking for the angular momentum around that origin point. And again, we can assume that the masses move along the xy plane. Okay, so like we don't really have the velocity components in z direction. So assume motion in xy plane, for example. Okay, and we are dealing with particles. You can really add more stuff, and we do ignore drag and everything else, so we don't need to worry about any of those. So we are assuming those velocities are constant, for example. Okay, so again, those R1 and R2 are given. So R1 is measured from the origin to the point mass 1, right? And R2 is from the origin again to where the M2 is. The direction is important. It's very similar to how we define moment arms in the rotation case. So this one is a little hard to estimate, but one thing I can say for sure is I can quickly check their directions, right? So when we find the angular momentum, there are two objects will have angular momentum, but angular momentum is a vector, so I have to do a vector algebra. And I can simply check if they're going to add up or subtract. So what do? I'm going to look into M1. So I'm following R1 and making a turn around V1. So that is a clockwise rotation. I'm going to do the same thing for M2. I'm following R2 and I'm making a turn around V2, and that is counterclockwise. So what I can see is that they will cancel out. Not maybe totally, because I don't know the entire algebra, but and another thing that I realized before in the previous clip is that I really just need the perpendicular component of V1, right? So that perpendicular component is going to be less than 5, maybe closer to 3. And if you look at R's, R2 is bigger, so maybe the angular momentum of M2 will have more angular momentum than the first one, and that means maybe the I feel like if I need to estimate, it could be counterclockwise. Okay, but I don't know for sure. Or if that if you look at the components, maybe it's going to be clockwise. So it's a really close call. It's hard to estimate in this case, but you can kind of think about it and then see what you think you may get. I can definitely see they will cancel out some, if not all. Okay, so let's start the solution. In the solution, so if you remember again, I reviewed the little bit of that cross product, and there are two ways to find cross product, right? The equation sheet has A cross B. It's just general A and B. In this case, we have R and P, right, instead of A and B, to find the angular momentum. So in the equation sheet, you have one of them as the determinant. So you just find it from the unit vectors. So you need to write them in unit vectors and then do a determinant and then solve for it, or plug into the equation given in the equation sheet. And the other one is using the magnitudes and then finding the angle between them and doing the algebra that way. But either way, the result is going to be a vector, and that's going to be angular momentum in this case. So it's a good practice. If you look at it in the solution, we're going to do both of them just to show you that both ways are fine. Okay, so in the first case, we're starting with M2, because this is nice that R2 and V2 are perpendicular to each other. So we are trying to find L2, and it's going to be, again, this is actually L2 is equal to R2 cross P, right? And what is this? It says P2, R2 cross MV2 not square, the vector, and M can be taken out, so this becomes R2 cross product with V2. Okay, this is where it comes from. And so again, we have a cross product right here, so let's just first try to do this in the first way, instead of writing the magnitudes. If it was up to me, I would just write the magnitudes. I wouldn't try to write them in unit vector notations, because vectors are easier to do that way. Like it would be just R2 V2 times M, of course, there's M in the front, and times sine theta. And sine theta is simply 1, so you can simply get that angular momentum that way, and then you can say it's out of the page, so it's going to be k hat, it's positive k hat because it's along the positive z direction. That's what counterclockwise tells you. This is positive, this is negative. Okay, but instead of doing that, we are going to write the vectors in unit vector notation, and then we're going to put things together and do a determinant to figure out L2. Okay, so we're doing it a long way, but it's a good practice. So what is R2? R2 is 3 meters, and what is the direction? Is along the positive x direction. So that is going to be 3 meters I hat. And V2 is along y direction, and it's 3 meters per second, and it's positive y, so it's going to be j hat. So we just write the equation, the vectors in unit vector notation. Now we're going to do the cross product. How do we do it? Again, it's a good practice. What we need is R2 cross V2, right? It's like that circled part in the equation. Later on, we need to multiply by mass to find the angular momentum, so don't forget that. To do this, if you focus on this cross product, we are gonna first write ijk as the first row. The second row is the first vector in the cross product, so it's R2. Only has x component. The j hat and k hat coefficients will be 0, and V2 only has y component, so it's only a non-zero term is in the j hat column. The rest is 0. Again, this part is coming from the equation sheet. Okay, you can just write that, or you can do the determinant. You're gonna cover I hat, right? So cover this one, and then you do the fish to the right, if you remember that. So you're doing this 0 times 0 minus 0 times 3 meters per second, and that's what you have in the parentheses, and it goes so forth. Okay, and the j hat, the fish is gonna to the left, point to the left. Back down here, and then you can write the determinant this way. But again, you don't need to memorize this. The equation is given. You just need to see which component is which. And once you do that, there's only one term that gives you non-zero, right? And it's simply coming from here, 9 meters square per second. Again, this is meters square per second. It's not the angular momentum unit yet, but one thing we find out is it's along k hat direction. So what you need to do, you need to also multiply by mass, because this was simply R cross V only, and that is what R cross V is, and multiply that by mass, then you're getting what L2 is. And again, we already figured that out using right hand rule. It was supposed to be along the positive k hat direction. For the next, we need to find L1 as well. Doing the same stuff. We are going to focus on, again, object 1, but we're going to do it just a little differently. And first thing we do is, again, we have R1 and V1. We look at them, and the angle between them is this angle here, 120, right? But we know that only the perpendicular component will be counted towards that angular momentum. So you can find that perpendicular component of V1 relative to R1. And using this angle of 60 degrees here, you can write it as V1 sine 60. So if that is what the perpendicular component is, and or you can also, again, you can do R1 V1 or mv1 times sine of the angle between them, which is 120, 60 degrees, not 120, because it's like R1 is that way, V1 is that way, this is the angle between them. So you can write L1 to be R1 P1 first, right, sine theta, and P1 is this, so you have P1 to be mv1. Instead of using V1, you can also use the perpendicular component, and that's what we are doing here, because V1 times sine 60 is that perpendicular component. Okay, so again, this is an extra step. You don't have to do it. You can just write it what it is, as just like I did here, right there, and then plug numbers in. Okay, you will get L1, and the direction of the L1 was clockwise. Clockwise gives you negative direction, negative sign, right? This is clockwise. That's why it's negative. So it's along the negative k hat direction. So it's into the page, not out of the page like L2. So when you're finding the total, what you need to do, you need to make sure that you keep those signs here. Okay, this is negative, this is positive because this is clockwise, this is counterclockwise. And then you just do the algebra, and you're getting negative. So it turns out L1 was much bigger than L2. So that's why the answer is going to be clockwise, because it's negative, as you can see. And that's the total angular momentum. So for rotation problems, we use angular momentum rather than linear momentum. And we see that it is a vector quantity just like linear momentum. It's a little bit more complicated because there's cross product, but torque concept really taught us well how to use cross product, and we are just practicing here. And this example shows how to calculate angular momentum, but it is likely the concept is still not very intuitive, because it's like there's 3-dimension, right-hand rule, and everything is playing a role. So for that reason, it was hard to estimate. Okay, so I could just say that they could cancel, but I didn't know for sure which one is gonna dominate.